Hi, my name is Jiazhi Guo, and I'm a graduate student from the National Taiwan University of Science and Technology. It's my honor to present my paper at Interspeech 2020. The title of my paper is An Audio-enriched BERT-based framework for spoken multiple-choice question answering. The authors are Jiazhi Guo, Shangbao Luo, and Guanyu Chen. This page gives an overview of my presentation. In previous studies of the spoken multiple-choice question answering task, it is a common strategy to take auto-transcribed text as the input of a text-based model. While the popular and powerful model BERT can achieve a certain level of performance, we propose a novel framework to incorporate acoustic features into BERT. In our experiment, our proposed framework can achieve new SOTA performance on a Chinese SMCQA dataset. So first, we want to define what is a spoken multiple-choice question answering task. Given a passage, a question, and several choices, all in the form of speech, the model has to select the correct choice from all the candidates. A common naive approach for SMCQA's task is by employing an ASR system to transform the speech signal into auto-transcribed text so that a text-based model like BERT can be directly applied to solve the problems. This is a figure of the vanilla BERT method. First, we concatenate the CLS token, the tokens of the question, the tokens of each choice, a SEP token, the tokens of the passage, and another SEP token. We pass this input sequence into BERT to obtain H, the contextual representations. Then we extract the H vector located at the CLS position and pass it through a fully connected feed-forward layer to obtain a RC-earn, which is a reading vector of this choice. So for each choice, we have to calculate all the RC-earn and stack them up and apply a softmax function to calculate the probability of each choice. So what we are trying to do in our study is that first we found that some study has shown that ASR errors could affect the performance of the SMCQA model. And we also found that acoustic features can offset ASR errors. So we try to incorporate acoustic cues with text level information. And here we take an example. If we have a token WI, and we are trying to extract its corresponding acoustic features FWI consisting of the little f1 WI to the little f WI WI, and the WI indicates the number of friends in these acoustic features. So how do we encode these acoustic friends, these acoustic features? We propose a novel attention mechanism called the TSAT, the temporal spectral attention. This temporal spectral attention layer first apply a fully connected feed-forward layer onto the acoustic features to obtain the WAFWI. Then a softmax function is applied on the WAFWI to obtain the attention matrix AWI. Then an element-wise multiplication is performed between the AWI and the FWI, and eventually we sum up these matrices along the friends to obtain the acoustic representation VWI. So with this TSAT layer, we want to use it in our BERT framework. So we propose another framework called AE-BERT, Audio-enriched BERT-based framework. First, we have input tokens, and also we have the corresponding acoustic features of each token. So the first thing we do is that we use our temporal spectral attention layer to encode the acoustic features to get the acoustic representation VWI, and we pass this sequence into another fully connected feed-forward layer to obtain the acoustic embeddings, the VHWI. Then with these acoustic embeddings, we simply sum up the acoustic embeddings and the token embeddings, also the segment embeddings and the position embeddings. Then we pass it through BERT to obtain an audio-enriched contextual representation. And in a similar manner of the vanilla BERT method, we extract the vector located at the CLS token and pass the vector through a fully connected feed-forward layer to obtain the reading vector called RCN. And also for each choice, we have to calculate its RCN, and we stack all the reading vectors and apply another softmax function to calculate the probability of each choice. And also, a pre-training stage is performed on the TSS layer. For each token WI, we have its token embedding EWI and its corresponding acoustic level representation VWI calculated by the TSS layer. We try to minimize the objective NSE between the VWI and EWI in our pre-training stage for the TSS layer. So here is the experimental setup for our experiment. We used 2018 Formosa Grand Challenge Talk to AI, which is a SMCQA dataset in Mandarin Chinese, consisting of a training set, a development set, and 2 testing sets, 1 elementary and 1 advanced test set. And it is worth mentioning that the advanced test set requires deep understandings. For the ASR systems we use Kaldee Toolkit and the TDNNF and the latest free NNI, and eventually our ASR system can achieve a character error rate of approximately 7.79%. So here is the first result we are showing here. We are trying to know that how many effects can ASR errors cause in a SMCQA task. We use vanilla BERT method here. First, on the left-hand side of this table, we see the data usage, the training, depth, and test. It can separate it into manual and ASR, which means the manual transcription and the ASR transcription. So what we are trying to do here is we're trying to fine-tune the BERT with the manual transcription and the auto-transcribed text respectively. And in our experiments, we found out that if we fine-tune the BERT with manual transcription, the BERT can actually achieve a really high performance on both the depth set and the test set, 18 and 91 respectively. But if we use the auto-transcribed text to fine-tune the BERT, then the performance will drop from 18 to 67 on the development set and drop from 91 to 77 on the elementary testing set, which indicates that the ASR errors is truly harmful in a SMCQA task. And the second table here is a comparison of different systems, including some baselines, some previous SOTAs, and our framework. So first, on the top 3 row, we see the QA-CNN, the HNN, and the vanilla BERT. We can see that the vanilla BERT can easily outperform QA-CNN and HNN because BERT is really powerful. but still it is a SMCQA data set. So our AE BERT, with the help of the acoustic features, it can outperform the vanilla BERT on all the data splits. And especially if we use the AE BERT with TS8 pre-training, it can outperform AE BERT without TS8 pre-training, indicating that the TS8 pre-training actually plays an important role in our AE BERT framework. So the conclusion of this study is that we propose another framework called AE BERT, the Audio-enriched BERT-based framework, which jointly considers acoustic level and text level information. We evaluate this framework on a published Chinese SMCQA dataset and acquire remarkable improvements over previous SOTA systems. This is the end of my presentation. Thank you for your attention.